Hello, everyone. Thank you for being here. My name is MICHALIS PAPADIMITRIOU. I'm a research fellow with the University of Manchester, and I've been working with the TornadoVM framework for quite some time. For you that don't know what is the TornadoVM framework, I'm going to get into it later during my presentation. So, how many of you did you follow any of the LangChain4j presentations these days? OK, we're going to do something different here. We're going to discuss about if in Java, if we have the tooling available to build the LLM inference libraries ourselves without having any external dependencies. And in this case, we're going to try to do it on GPUs with TornadoVM. So let's ask the question, do you think that Java, how it's doing with the AI race? Think a bit about it. I'm going to get into my answer later during this presentation. OK, so what's happening right now? So many of you maybe have seen the LangChain4j that provides integration with all the LLM vendors. So it's very easy to build agents. You can have your microservice, Quarkus, Spring Boot. Then you can have LLM directly working with your application. And they have very good coverage. They support vector databases for storing embeddings. But also they have support for all the major LLM vendors like ChatGPT, Anthropic, OpenAI, Mistral, Vertex AI, all these kind of things that most likely you find yourself using. This is very good when we want to run things on the cloud. But because it's a domain that it's shifting very fast, what we've seen is that there is a demand for running models locally on your machine. And one of the greatest examples is, I don't know, how many of you have used the IntelliJ, the latest feature of the autocompletion? OK, this pretty much what's happening is that you're having a small model trained in a smaller data set that, based on the prompt, on the fraction of the code that you're running, you're getting some responses. So what's happening, it runs locally on your machine because we have things like we don't want our code to be used for training other model. And then eventually you run up into cases like having your code coming back from ChatGPT online when someone asks a question. And this is not limited to that. We have other things like to think about privacy, GDPR, security. And we have many people that they want to train their own models in smaller data sets and just serve a very specific purpose. So obviously, we cannot do that online. And for Java right now, what's happening is that we have a large selection of frameworks that most of them, they use wrappers usually. So you have Java bindings, wrappers, usually JNI so far, and two native AI frameworks. And what is really dominant at the moment is the Onyx runtime, because it has a very good stable support for the JNI bindings. And other things like PyTorch, TensorFlow, they have Java bindings as well. And then we have also Java libraries that they use JNI, DeepNet's Deep Learning 4j. So from this, we start asking some questions. So do we have a PyTorch? PyTorch has been dominating the AI frameworks, but do we have something equivalent in Java? And if yes, or if we want to build something like this, how we can achieve high performance inference in Java? Also, another interesting topic is the AI training, but we can discuss in another day. So today, we are focusing here on how we can build libraries for high performance LLM inference in Java. To do so, we need to have a look briefly about what native frameworks they've been doing. And actually, what they've been doing great is that since the Llama 2 architecture came out last year, they built a vibrant community. So we have the main two projects that they drive this to the community. That is the Llama C++ implementation and the Llama 2.c implementation. So they stripped down the requirement of having a GPU to run a large language model, and they boiled it down to the fundamental algorithms, and they purely implemented it in C. And then you can find inside things like OpenMB, vectorization, and then you have a pretty fast CPU inference. And then on top of that, we have the Llama library, which uses, for example, the Llama C++ implementation as a backend to generate the code for the CPU inference. And then LangChain has a port, for instance, for the Pythonic world for the Llama. So things came naturally for the native libraries. And because they have very large communities, they have immediate support for all the major models that you've seen. So from the Java perspective, you need to have API calls to the LLM vendors, but for the native, you can directly invoke the models. But here we are mostly interested for Java, and let's see what Java does. And apparently, a few folks out there, they got these implementations that are fully built in C, C++, and they try to put them from the Java perspective. So we have two different groupings. Either they went to the pure Java implementations, or they use wrappers. So in the case of the pure Java implementation, they use the latest advancements that you can find in OpenJDK 21, for instance, like Vector API, that is 7 incubator, and Project Panama, that for you that you're not familiar, Project Panama, among other things, it's an extension of what we had with the direct buffers and what we had with the JNI, so it provides a more natural way to interact with external libraries and with off-heap data types. And in that case, both of these approaches, what they used is that they used Project Panama and Vector API to mitigate the computational bound. And then we have the Java Llama C++ implementation that uses JNI directly to the Llama C++ implementation. So has GPU support, quantization, support for the latest models. But again, we have wrappers. And then we have the Llama2j that uses the JCUDA implementation, which is a wrapper for CUDA code. So you need to write your GPU code yourself, wrap it into a string, and then write also all the utility functions to offload it onto the GPU. All these are available online. And also what I skipped is that the first implementation also has support for GraalVM native image, which is interesting in case that we want to have a pure Java implementation, bundle it with a microservice and run it locally in our machine. So at this point, I'm gonna be brave and try my first demo. So what I tried is that we got the Llama 2 Java implementation that's out there on the open source, and I selected a large model from a selection that's called the Tiny Llamas, which is a dataset of a small stories that it generates. So it's based on the same architecture, so it has the same compute and memory requirements as a big LLM, but it's trained to serve a very domain-specific purpose. And I choose to use this model because I think it reflects with the kind of requirements that most likely we're going to have from the Java perspective if we want to have CPU inference running locally. So let's see. OK, so here I have my IntelliJ. I just clone the repo. I download the requirements. I download the model. And then I have it here running. So I provided an empty prompt to it. So it's going to generate a small story based on the model that it's been trained on 110 million parameters. So here we see the story, and then we see also a number of tokens that it generated per second. So we cannot trust the performance because I ran it on my CPU and now I have many things open. But trust me, this is what it does. At this point, I think what is mostly interesting to us is to see about its performance. And I'm going to run it again with the IntelliJ profiler to collect some data, because I really want to see where the most time is consumed when I'm running the inference locally from Java in my machine. So by looking into the results, we see that the majority of the execution time is spent in these methods. This method that's called matmul pretty much is the core of the computation of the CPU of the LLM inference itself. And as we look into it, we see that already it's been optimized highly. So we see that we have a parallel stream. So it's utilizing, from the configuration, and you can see that it's utilizing all of the cores available in my machine. It's the original thing, it uses direct buffer, so it gets the memory segment from the buffer, and then we have the vector API doing a vector addition, but it doesn't stop here. So we can see that the original author did some other tricks, like unrolling manually the accumulator, and also using the FMI instruction. So if you previously today you were in the vector API presentation, you see that along with the vector API you have a set of intrinsics that they map directly to hardware, so you can speed up of things. But obviously this is not for the average programmer that wants to do these kind of things. It needs to have some notion about also for the hardware that you are running. And yes, so this is the main, let's say, computational bound of the application. But let's see what kind of performance we achieved by running that. So we ran some things in isolation. So from the tiny llamas dataset, we got 3 different models, varying from 15 million to 110 million. So again, we want to most likely reflect for the cases that it makes Java relevant to run CPU inference locally. So very small domain-specific models that we are going to wrap them in a microservice and share them in an edge deployment or something that it makes sense. And we compare the results with the Llama 2C implementation, the one that we used as a reference from the beginning. And it uses, for the same method and the computational aspect of the problem, it uses OpenMP, and also it's compiled with all three flags. So we assume that that has auto-vectorization enabled. And what we see is that for a small model that we're still on the compute-bound side of problems, the Java, the highly optimized, let's say, Java CPU inference has about 50% parity in terms of performance for tokens achieved compared to the native implementation. But as the problem size increases and we go from being compute-bound to memory-bound, we see that the highly optimized Java with Vector API and Project Panama has about 90% parity with the native implementation. So we see that for CPU inference, it might make sense to have a Java library to do the CPU inference and also get some benefits from that and to have full control on the objects and the data and manipulating and having some pipelines that we can do also the pre-processing and post-processing of the data of the model. So based on this, again, pretty much here sum up what I already told you, that this is the main, where the most time of the application is spent. And we managed to achieve 90% parity because of the FFM, Project Panama, and the Vector API. But going from this we come to another question about how can Java become AI competitive and start building our own tools and libraries and reducing the dependency to native AI frameworks. And my team, we've been working on Java and GPUs for almost 10 years now. So we started from the project TornadoVM. So we come up with these 3 pillars, how we call. So if we want to build AI competitive libraries for high performance inference in Java, we need these 3 things. Somehow to provide GPU acceleration. We need to have a standardized tensor type. It's what Python frameworks they've been doing for quite some time now. And we need to have interoperability and integration. And if we want to look further into that, we're living in a great area for Java because we have a selection of, no one could imagine 5 years ago that we have not just one framework, but 2 different frameworks and working on bringing GPU acceleration into OpenJDK. So TornadoVM does that. Project Babylon does that as well. That's for the GPU aspect. And regarding standardized tensor types is something that we are missing, because if you remember what I told you on the very beginning, that we have a selection of Java wrappers to different frameworks. Then we have libraries like deep learning for J, deepnets. All of them, they implement their own data types, their own data structures for something that for the Pythonic world has been already standardized, the notion of shape and the arrays. So we currently were missing that from Java, because if you commit for one approach, then you are bounded to it. Other, you need to rewrite your application, rewrite your data structures and stuff. So potentially we can have a JSSR to standardize the tensor types. And I think we can base that on Project Panama. Memory segments, it's a great baseline to have this interoperability, and eventually Valhalla. Then we can use these data types to have interoperability and integration with Project Panama itself, the Vector API, GraalVM, direct buffers, ML frameworks that they have Java bindings, LangChain for J, deep learning for J, and more libraries, because we expect that more libraries are going to start showing up in the Java ecosystem. And now I'd like to revise these pillars with some practical examples. And what we did here is that we got the Llama to Java implementation that I showed you already, and we used TornadoVM. So what we did is that we import TornadoVM. As I mentioned already, we found that the most time spent it was in the matmul method. We have 8 different invocations of this method with different data sizes. So we opted in just to try to accelerate and offload to the GPU only the final invocation, that it has it operates on the largest chunk of data. And this is because we want to showcase that we can have synergy with Vector API and other features of OpenJDK. So it doesn't always, it's not always necessary to run things on the GPU. So let me run it. Okay, live demo. Where is it? Okay. That's why I have my runner script, just in case. Okay. So now we run the same example, the same inference, but now it runs with Tornado. So what it does is it's going to offload the last method to the GPU. And it's not very invasive, the change that we did. So the only difference is that the weight tensor that holds the whole vocabulary, which is the largest chunk of data for this model, we copy it to the GPU just once. And then on every iteration, we're just reusing the data. So we don't have I/O every time that we run the GPU. So, okay, let's revise the numbers that we showcased before. So as we can see now, we have an extra field that we get some reference numbers with Tornado. And that we see, obviously, the performance benefit is not great because we're having a GPU running, but it's about 8%. But we see that we close the gap with native. And when the problem becomes memory bound, we see that we have about 99% parity with the native implementation. So I think we have some key observation from this thing, that even by not having a very sophisticated rewriting of our program to be GPU efficient, we managed to have an 8% improvement and close the gap with native. And also we have seamless integration with the Panama and Vector API, because we showcase that it doesn't make sense to offload all the invocations onto the GPU. We can do it when the data is sufficient to have some benefit. And we get almost parity with native code. So what is TornadoVM? TornadoVM is an open source framework to allow GPU execution for Java. It's been out there for almost 10 years now. It has documentation online, the repo is online. We have plenty of examples. But because it's been out there for quite some time, it has an ecosystem around it. So it has support for the latest JDK 21. Most likely for any kind of OpenJDK JDK that you might be using, it supports Tornado. It's just a plugin for an existing JVM, so it's another dependency in your POM file. So it has OpenCL, SPIRV, PTX backend. Regardless of the hardware that you have, most likely you're going to be able to use it with Tornado. And because it's built on top of Graal, you can use Truffle and then find yourself running JavaScript, Python, Ruby, R, Scala onto the GPU as well through the same APIs. It has Docker images for NVIDIA, Intel, a plugin for IntelliJ that gives you some programming hints, and it's smoother the transition on its programming model, and soon it's going to have support for JDK 22 as well. And now that we've seen the potential benefits, we stepped a bit back and we tried to design our own tensor types because, as I mentioned, it's something that is missing from the JVM side of things. So we wanted to have what we call the tensor API. We wanted to use FFM and Project Panama as a baseline, have compatibility with Vector API, being able to interact with ML frameworks that have Java bindings, like Onyx, for example, and obviously get the benefit of GPU acceleration through Tornado. And in order to do so, we need to have a sense of what is a tensor. So tensor pretty much is a multi-dimensional array that is characterized by three things, so a rank, a shape, and the data that it holds. So the rank is the number of dimensions, the shape is the elements that you hold in every dimension, and the data type, it's the type of data that you have. So with this in mind, again, we want to be based on Project Panama and having compatibility with Vector API, TornadoVM, and ML frameworks. So in the first version that we introduced, we come up with this definition of a FP32 tensor. So this holds float data. It has a specific shape, a number of elements, and underneath, in the tensor storage, we store it in the consecutive segment in memory through Project Panama. So a float array is just a wrapper to a memory segment that stores float data off-heap. And on the right-hand side, you can see that we have a three-dimensional shape of 64 elements in each dimension. We have a tensor fits this shape, and we initialize it with a constant value. And from this notion of tensor, we had the whole collection of it. With the yellow, you can see all the support for primitive types. And with the red color, you can see the FP16 tensor. So we start thinking about how to support quantized models. And with gray, we have tensors of quantized types like int4, int8, things that you can have in the GPU, and we want to be able to map them directly from the JVM world to the GPU code generation. And also for this, we have methods for memory management, like get the segments, get the direct buffer, going back to heap arrays, and also constructing tensors from segments or from direct buffers. So we want to have a more natural way to interact with existing applications. And we managed to do that with Onyx runtime, and I'm going to show you an example later on. Also, we looked into the Pythonic world and what kind of operations. So we support also an initial set of tensor operations like initialization, concatenation, slices, and all this by providing wrappers to the Project Panama and working directly with segments. So we want, for people that have worked this kind of frameworks before, to have a natural transition, and if they want to try to code something with the Tensor API, to feel more natural. And now it's my time for the third demo, let's say. So in this demo, what I would like to show you is that we can have the same data structure, the tensor. So here we have a two-dimensional shape with 16 elements each dimension. Then we have a tensor A and tensor B. The shapes are matching for both of them. We initialize tensor A, and we initialize also the tensor B with induction variable plus constant value. And then we perform a vector addition between the two tensors. So we want to replicate this addition with normal on-heap operations with vector API and on off-heap types, and also with TornadoVM on GPU. So here, if I run this example, we can see that we get the output of the vector addition, and also we have some helper utilities to dump the shape of the output tensor as in Onyx and as in TensorFlow, just in case for people that want to run the cross-check and reference implementation. And now we are going to do the same tensors, but now the vector addition, instead of running on on-heap, we are going to run it through the vector API. And we're going to invoke the segment for its tensor and operate on the segment off-heap and running the vector API. Same output, same results as before. And now we can do the same thing with Tornado. So again, we can use the same data structure. We don't have any difference. And we directly invoke the TornadoVM API, which shows which data structure we want to offload in the GPU and which data structure we want to copy back from the GPU. And here is how we express the same vector addition through the Tornado API. So as you can see, this is much simpler now. I'm going to run from here because I have a... Again, you see that we get the same output, and the other difference is that we enable debug information to verify that things run on the GPU this time. And the final compatibility aspect is Onyx runtime. So we use the Java bindings for Onyx runtime. And we got a model directly from Hugging Face. It's a MobileNet, it's a computer vision model. And we create a tensor, a 4-dimensional in this time, and we're going to run the inference of the model based on this. And here we get from the tensor the direct buffer, because Onyx runtime right now supports only direct buffers and not segments. And here we see that we managed to run the inference, and then we have the output objects, and then if we have find ourselves working with the Onyx runtime, we can use the object. So going back to my original question, I don't think that the Java is losing the AI race, but it's just the beginning. And I think it's because now we live in an era that we have all the components available to build this kind of AI libraries in Java. So we have core projects like Panama, Valhalla, Babylon, Vector API, the GraalVM, its native image, and GPU acceleration through TornadoVM. We have a lot of frameworks that already they have support, like LangChain4j and DeepNet, Deep Learning 4j, and they provide the interoperability with the AI frameworks through wrappers. And what we are missing, I think the key component is having a tensor type or a data structure that it can be, the glue between all this, and start implementing AI libraries in a more natural way for the Java ecosystem, and reducing slowly the dependency to the native libraries. So everything is online, all the code, TornadoVM, the API demo, and the integration with the llama2.java, and also the original llama2.java code that I used for the demo. And yeah, thank you. So